Time. Hopefully not a boring video time. Here we go. So the first thing, you're going to like this part. So you see where it says integrated rate laws on page 35 and 36 and 37? That's actually no longer IB covered. There's some interesting stuff in there. You can see this graph here on page 37. It shows a first order reaction, first order decay. You may have seen something like that in math. It actually means that the reaction has a half-life. You can see that half of the original concentration is used up in 100 seconds, and then the next 100 seconds it's another half and half and half and half and half and half. But we're not going to do that. Instead, I want you to go directly to the bottom of page 37, and we're going to talk about reaction mechanisms. And so you'll have to pause this video along the way and give it some, give yourself some opportunity to work together. I'll feed you some more stuff perhaps than I would have had we done this in class, but be that as it may, we'll just get through it. So reaction mechanisms. Most chemical reactions occur through a certain multi-step pathway. This is called a, go figure, reaction mechanism. And this is what many people consider the holy grail of chemical kinetics, understanding exactly how a reaction goes step by step, collision by collision. Very hard to prove, actually. We're going to talk a little bit about that a little bit later on. But first, I just want to give you what looks like a very simple reaction. NO2 and CO goes to NO and CO2. So essentially, if you look at it, it's just an oxygen transfer, right? You get an oxygen going from the NO2, goes to the CO, and you're left with this. That's not actually how the reaction goes, but I want you to play the game with me right now. I'm going to tell you, remember, rate laws can only be determined experimentally. But I'm going to tell you that the rate law is second order in NO2 and zero order in carbon monoxide. So I want you to write the rate law right now. So press pause, get in groups of, 4, 3, 4, or 5 is fine. And move your desks and press pause and write down the rate law. Make sure you all have it. So pause. Okay, now you're back. Here is the rate law. Rate, you should have this already. Rate equals K N O2 squared. That's what it says. CO to the 0th, which would be 1, so rate equals K NO2 squared. So this is going to be the basis for our work. Now, how did you know that that's the rate law? I told you. Okay, you wouldn't be able to do this any other way except experimentally. So go to page 38. And what I'm going to tell you is that this isn't the whole story. I'm going to give you a proposed mechanism where you have, so you can take a look. This is the overall reaction, but the proposed mechanism has 2 steps. First, a couple of NO2 molecules collide, making NO3 and NO. And then an NO3 finds a CO, and that makes NO2 and CO2. So notice the NO3, which is not in the overall reaction, shows up here being produced and then used up in a reaction. So what is that called? Something, a material that is made and then used up in the reaction. So it doesn't appear. It's not a reactant or a product. What is it? Press pause. Okay, you're back. Let's see if you come up with it. If you don't know, let's see. It's 1, 2, 3, 4. Well, I was going to play Hangman, but forget it. It is an intermediate. Each of these reactions that's listed right here is called an elementary reaction. Okay, so an elementary reaction is actually a pretty special kind of reaction, and it's only one that is shown in a proposed mechanism. And the thing that makes those types of reactions special is that you can actually write the rate law from the reactants. So it is an elementary reaction is a reaction step from which a rate law can be written by changing coefficients of the reactants into exponents. Something that you may have been interested in doing before, but I caught you in that hydrogen-bromine example where things went absolutely haywire, right? Remember the one that was like the iodine was H2I2, but then the bromine one was H2Br2 to the 3 halves over Br2 plus K prime HBr, crazy stuff. And the whole point there, what I was making, is that rate laws can only be determined experimentally. And while that is true, once you propose a mechanism, as we're going to find out, that mechanism has to agree with the observed rate law. And so these elementary steps, you can write the rate law by changing the coefficients of the reactants into exponents. So we're going to see how that works in a second. So molecularity is the number of blank required to collide to produce a reaction written. Come on now. Context. Molecularity is the number of... Okay, I think you actually got this one. I'm going to make a wild guess and say that you got molecules. They're required to collide to produce the reaction written. Unimolecular. How many molecules is that? 1. Right. Okay, so let me give you an example of a unimolecular reaction, which is one molecule. So we have A goes to products. And what I'm saying is that you can write a rate law from that by changing the coefficients into exponents. Now, this coefficient is only a 1 here, so rate equals Ka. Notice I just took the reactants in this reaction. Now, I'll show you how this works with a bimolecular reaction to make it a little bit more obvious as to where this is all headed. Bimolecular. So, an example of a bimolecular, how many molecules would that be? Oh, awesome deductive logic, it's 2. And so A plus B goes to product is one possibility. If we were to do that, the coefficients are still 1, so it's pretty straightforward. Rate equals K A B. And now I'm going to give you another possible reaction that's bimolecular like this. 2A goes to products. I'm going to press pause, and I want you in your groups to figure out what the rate law would be for that. So press pause. Okay. But now you have a coefficient, or it's A plus A, which would have come out A times A. But if it's 2A, you can just change it into A squared. But I want you to notice that if I had written this as A plus A, which of course is 2A, it would have been K times A, which is still Ka squared. So really I haven't done anything different here. It's just that this is like a shortcut that happens if you have coefficients. So now I want you to do the term moleculars on your own. I want you to come up with 2 possible term molecular reactions. Term molecular would be 3 molecules. And I want you to write the rate laws associated with them. Now, I have amazing faith that you did great work. So excellent work, y'all. But did anybody happen to look at the next page and all of them were right there? Yep. So right there on the top of page 39, you will see that there are examples of elementary steps and the rate laws that come from each of these elementary steps and explanations about how the coefficients derive into the exponents. So now you have a bit more of an understanding about how a reaction mechanism is set up. It's a series of elementary steps or elementary reactions. Those are synonymous, which meet 2 requirements. And you're going to check the first one right away. The first requirement is that the steps must add up to the overall reaction. I mean, it's kind of obvious, but it has to be said. If the steps don't add up to the overall reaction, it can't be a mechanism for that reaction. So you're going to go back to the example in a second. And the second thing is that the mechanism must agree with the experimentally observed rate law. That part we haven't really discussed yet and how that might be fleshed out, but I'm going to show you that in a little bit. First of all, though, I want you to go back to your example, the one that we've been working with, and see how we're doing. So the overall reaction is back here on page 37. I'm going to scroll up now back to page 37. This is the overall reaction. NO2 and CO goes to NO and CO2. Here is a proposed mechanism on the top of 38. What you need to do is write these reactions down on the bottom of 39 and verify that when you add them up, you get the overall reaction. So go ahead and verify that. Remember, it's just like Hess's law. You're going to cross out what is on both sides. So press pause, do that. Okay, you probably have been able to see that if you do this, NO2s, and one of the NO2s crosses out with that one, and the NO3 goes out with that one. So there you go. Come back to the next video for the rest of the story.